Up to now, we've been talking about whether or not a reaction is spontaneous or not, or the energetics of a reaction. We know that spontaneous reactions are likely to happen if given time. We haven't said anything, though, about how much time. How fast a reaction can happen is all about the kinetics. And the speed of a reaction is dependent on three things. And I paraphrase here. The reactants must first meet. So the reactants must meet. That seems like a no-brainer, right? Next, the reactants must meet with the right orientation. Orientation is a very big part of making sure that a given reaction happens. And finally, they must meet with the right amount of energy. So there are a bunch of things that we can do to increase the speed of the reaction. We can increase the concentration of reactants. We can add a catalyst. That will certainly help the orientation piece. And we could certainly run reactions at higher temperature because everything has higher energy at a higher temperature. Now, how do we measure how fast a reaction is? The measurement of the speed of a reaction is something called the reaction rate. And it is measured as the change in concentration. So that's what is on the y-axis here, change in concentration, which, as you know, should be measured in molarity with respect to time. And time can be in minutes or seconds or hours, depending on what we know, how long a reaction is likely to take. So concentration versus time. Now, I can measure the change in concentration of products compared to time or reactants. If I do a measurement on products, I can see that this is going to lead to a positive rate. That's because the concentration of products are going to grow in over time, whereas the concentration of reactants are going to be decreasing with respect to time. So any measurement of rate with respect to reactants is negative, and with respect to products is positive. But certainly, either is an acceptable measurement of rate, showing how products increase over time or reactants concentrations decrease over time. For a given reaction, so we're going to make a generic reaction here, and we work a lot with generic reactions when we're talking about kinetics. There will certainly be more specific examples on your homework sets and everything, but it's pretty easy to work with generic reactions. I can measure the rate of the concentration of A with respect to time. So concentration of A with respect to time is going to look something like this. Now here's the problem though. I can measure the rate as an average rate, or I can measure the rate at a very given moment in time. Usually we take what's called the instantaneous rate. The instantaneous rate focuses on the linear area of this curve here. And what I do is I make a sort of a line tangential. It's not the best tangential line, but hopefully you know what I mean. That is a measure of the instantaneous rate. And I take the slope of this line. Okay, so I take 2 points on this line, and I'll get the slope, rise over run. Okay, so my distance, my y2 minus y1, x2 minus x1, or the slope of this line that's tangential to the linear portion of my curve is going to be my measured rate. And my rate, I know, is going to be equal to a negative change in A's concentration with respect to time. Now, we don't always give a rate that's a measurement with respect to a given component, but sometimes we give a generic rate. A generic rate is always the absolute value of any rate that's measured. So if you needed to get back to a rate with respect to a reactant, you'd need to apply a negative sign. You wouldn't have to apply a sign if you were looking at the products. But certainly, we always want to take any coefficient component out of it. So a generic rate, if I wanted to give a generic rate, would be the absolute value of this rate, and I would divide by the stoichiometric factor with respect to A. And this would give me a generic rate. If I wanted to get back now to a rate with respect to B, I would apply a negative sign, and I would multiply by the coefficient that is in front of B. That would be lowercase b. All of this is great. All you really need to know is that rates are measurable entities. And the measurement is going to be the change in concentration with respect to time. Again, the sign doesn't matter. The sign only helps us understand if we're talking about reactants or products. Okay, so measuring the rate is very useful. However, the rate law is much more useful. So here is a generic rate law that we're going to talk about, and this is one of the very first must be able to do in the kinetic unit. So here is our rate law for the generic reaction that I had on the previous slide. Okay, I'll write that down just here at the bottom of the slide. So here is my reaction that I was looking at. Okay, great. So here is what we would call a generic rate law at the top of this slide. This here is the measured rate, and again, the rate can be measured with respect to any component of the reaction. Julia, pardon me. As you can see, things are never easy at home. Okay, where were we? Rate is the measured rate, so we can measure that with respect to anything. This K value is what we call the rate constant, and the rate constant's units change dependent on what X and Y are, the superscripts for the concentrations of A or B. What you should know about the rate constant, it is a constant for a given reaction at a given temperature. Okay, here obviously is the concentration of A raised to some power X. We call this the order X, actually, and Y are the orders of the reaction with respect to X and Y. Basically, this tells me how many of these reactant molecules interact in the slowest step of a mechanism. This is something we will capitalize on more in our second lecture on kinetics, but suffice it to say that I do need to know what the order of the reaction is for X and Y. So, or for A and B, pardon. X being the order of the reaction with respect to A, Y being the order of the reaction with respect to B, and X plus Y is the overall order of the reaction. What you can see then is that the measured rate is equal to some rate constant, a proportionality constant, times the concentration of A raised to its proper order, times the concentration of B raised to its proper order. Okay, let's move on from here. The overall rate law, very, very important, must be experimentally determined. That is the only way to get the rate law. Here are the steps that we're going to take to determine the rate law. First, we need to find the orders of the reaction with respect to any reactant. If you have 3 reactants, then you'll have 3 orders. If you have 1 reactant, you'll have 1 order. This is the first thing that we're going to do. So we find the orders of the reaction using experimental data. This is what we're going to start on the next slide. The second part of this is to use a single experiment then to find the magnitude of K, the magnitude of the rate constant. And finally, we're going to determine the units of K based on the orders of the reaction. So these are the steps that we're going to apply to some data that I'm going to have on the next slide. Okay, so that will be slide 6. I will be constantly referring back to slide 6 as I'm calculating the orders of the reaction for my given reaction and the rate constant. Okay, so here is the data that we're going to use. For the same generic reaction, A plus B, these are the coefficients, and then the reactants themselves gives me C plus D. I'm going to figure out what the order is with respect to A, that's X, what the order is with respect to B, that's Y, and the rate constant. Here are the experiments that I'm going to use to do it. I have 4 experiments that I'm going to do for this, okay? Probably only really need to use 3 of them, but we could add a 4th in, see how much more information you can gain from this. Okay. So here is the information I have. Okay, so here are the concentrations of A in each of these experiments. 1.25 molar in the first, 2.50 molar in the second, 2.50 molar in the third, and 3.47 molar in the fourth. Okay? The concentrations of B are 1.25 molar in the first, 1.25 molar in the second, 4.29 molar in the third, and 2.18 molar in the fourth. The rates of the reaction are as follows. 9.1 times 10 to the minus 8th in the first, 1.82 times 10 to the minus 7th in the second, and 2.14 times 10 to the minus 6th in the third. You're going to calculate that for the fourth experiment. Okay, so on the next slide, I'm going to begin to start figuring out the orders of the reactions with respect to A and B. Slide 7. Finding X, the order of the reaction with respect to A. I'm going to use experiment 1 and experiment 2 because experiment 1 and experiment 2, the concentration of A changes, whereas the concentration of B does not change. So I'm going to write out the generic rate law for experiment 1 and divide it by the experimental rate law for experiment 2. So the rate of experiment 1 is 9.1 times 10 to the minus 8th. And that's going to equal some rate constant, the concentration of A, which is 1.25 to X, and the concentration of B, 1.25 to Y. I'm going to divide this by, now, the rate law for experiment 2. 1.82 times 10 to the minus 7th times the rate constant, the concentration now of A raised to the power X times the concentration of B raised to the power Y. That does say 1.25 there for B. Now, what cancels is X because they're the same, and 1.25 of the Y cancels as well. Excuse me. So what I get in the end is the ability to calculate now the reaction rate with respect to X. Let me get a calculator and we'll calculate that. Okay, so if I do all the division, 9.1 times 10 to the minus 8 divided by 1.82 times 10 to the minus 7, I'm going to get 0.5. And this is going to equal now, oh, look at this, 1.25 divided by 2.5 is 0.5 raised to the x power. I can already see that x is equal to 1. Great. I have my first order of the reaction calculated. I'm now going to figure out the order of the reaction with respect to B, or superscript Y, on the next slide. In this case, I want to use experiments 2 and 3. Here, the concentration of A stays the same, and I'll be able to cancel that out, but the concentration of B changes. So, I'm going to divide the experimental rate law for experiment 2 by the experimental rate law of experiment 3. So, experiment 2 has a rate of 1.82 times 10 to the minus 7th, and that's going to equal the concentration of A raised to X. At this point, I could put in 1, it doesn't matter, and the concentration of B raised to the power Y. I'm going to divide this by the rate law of experiment 3, which is 2.14 times 10 to the minus 6, and that's going to equal now 2.5 to the raised to the x and 4.29 raised to the y. I can see that my order with respect to x, so A cancels, as does K. Oh, I forgot to add K. That's not good, but K cancels as well. So what I'm going to get here, once I do my math, 1.82 times 10 to the minus 7 divided by 2.14 times 10 to the minus 6 is going to be, I'm getting it right now, 0.085. I'm going to check that one more time. 1.82 times 10 to the minus 7 divided by 2.14 times 10 to the minus 6, and that gives me the same number. Okay, and I have 1.25 divided by 4.29, that's the concentrations on the other side, excuse me, so that's going to equal 0.291 raised to the y. Now the way I solve this is I take the natural log of each side. When I do that, I get the natural log of 0.085 is going to equal y times the natural log of 0.291. So y is going to be the natural log of 0.085 divided by the natural log of 0.291. So I'm going to figure that out here. Divided by the natural log of 0.291. And that's going to give me a value of 2. So the order of my reaction with respect to B is 2. Okay, great. I'm almost there. I now need to find the magnitude of K. I'm going to do that on the next slide. So I'm going to choose a single experiment to do this. The single experiment I'll choose, let's say, is experiment 1. So here I know the rate of, when I mix those concentrations together, is 9.1 times 10 to the minus 8. And I know that K is going to equal the concentration of A, 1.25, raised to the first power, times the concentration of B, raised to the second power. That's putting in the value of X and the value of Y. Now if you can see, I have one equation, one unknown. So if I take the rate, 9.1 times 10 to the minus 8, and divide it by 1.25 3 times, that's going to give me now a magnitude for K of 4.7 times 10 to the minus 8 times 10 to the minus 8. So that's the magnitude I have for K. Now let's put that all together. My generic rate law is going to be as follows. A rate is going to be dependent on 4.7 times 10 to the minus 8. I still need to put in units here, so hold on. The concentration of A raised to the first power and the concentration of B raised to the second power, which means now if I plug in my concentration of A or B, or A and B, I will be able to determine the rate. So if I change the concentrations of A and B, I will be able to determine easily the rate for that given experimental condition. Now you can see that A and B is really, if I think about the units, molarity to the third power. And I know that the rate needs to go back to molarity per second, which means my K value must be units of molarity squared seconds, because this is going to cancel 2 of those molarity units and wind up with units that are molarity seconds, which is, I know what the rate is. It's measured as molarity seconds, which means the units for my rate constant, because it's third order overall, x plus y equals 3, third order overall, is going to have to be m to the minus 2, s to the minus 1. Those are my units for K. And now, this whole thing that I'm boxing is my official rate law for my reaction. Very exciting, isn't it? Just look at that boxed entity. Okay, great. Now, what do we do with this sort of information? We can actually do a lot with this sort of information. On the next slide here, we're going to discuss just a little bit of this. First, if I were to given concentrations, I would be able to figure out the time it takes for a reaction to occur. That's pretty good. I can also use this rate law to figure out the mechanism of a given reaction. That's also pretty amazing, but that is the focus of the second lecture in our kinetics unit. Today, for the remainder of this lecture, we're going to focus on how to calculate this concentration versus time. If I knew how long a reaction was taking, do I know what my concentration is in the end? Vice versa, if I know my concentration, do I know how long it's going to take to get to a certain end or final concentration? Okay, we're going to start that on the next slide. All right, so let's start with what you're going to be held responsible for. You're going to be held responsible for 2 simple processes, 2 simple types of reactions. Both of them fall into the one singular reactant, we'll call it A, leads to products. The first simple process you're going to be held responsible for is what we call a first order reaction. I hope you recognize that means that the order of the reaction with respect to A is equal to 1, which means our rate law is going to look something like this. The rate is equal to K times simply the concentration of A raised to the first power. This is the first simple process you're going to be held responsible for. It is a decomposition process where A decomposes to give products, where the rate is first order with respect to A. The second simple process that you're going to be held responsible for is where we would call the reaction a second order process. Second order with respect to A, which means that the rate of the reaction is equal to K times A squared. So how are you going to know if it's a first order process or a second order process? The rate law could be given to you or you've determined it. If you determine that the order of the reaction is 1, then it's a first order process. If you've determined that the order of the reaction is 2, you know it's a second order process. You can certainly figure this out from the units of the rate constant, which should always be given to you. The rate constant for a first order process is always going to be seconds to the minus 1, and only that. You should be able to figure out why that is. And the units for a second order process rate constant is going to be molarity to the minus 1, seconds to the minus 1. So if the rate constants are given to you, you'll be able to figure out if it's a first order process or a second order process. Now there is a way to do this graphically as well, and I will come back around to that. Okay, so I say you're going to be responsible for them, but what does that really mean? That means you're going to be responsible for being able to calculate concentration if given information like the rate constant and the time the reaction takes, or to calculate the time if the initial concentration or final concentrations are given and the rate constant is given. Basically, you need to use the integrated rate laws. The integrated rate law for a first order process is as follows. And this is an integral, it's an integration here. So it winds up being the natural log of A at some time t. This is what it means. The concentration of A after a certain amount of time has passed it is equal to minus kT plus the natural log of the initial concentration of A. This is the integrated rate law for a first order process. Again, let's describe what all these variables are. The natural log of A after a certain amount of time t has passed is going to equal negative rate constant K, must be given to you in the problem, multiplied by time. Make sure that you use time in the same units given to you in the rate constant, plus the natural log of the initial concentration of the reactant that's undergoing decomposition. The second integrated rate law that you're responsible for is for the second order process, and this is equal to 1 over the concentration of A at time t, and that's equal to kT, no negative in front of K, plus 1 over the initial concentration of A. Okay, these integrated rate laws give you a sense of how else you can calculate whether or not a process is first order or second order. If the process is a first order process, that means that the natural log of concentrations at given times, okay, compared to time, so this is y and this is x, time, will give you a slope of k that should be a linear equation. Do you see how y could equal the natural log of concentration of A at a given time, equals m, that's the rate constant, t, that's the x variable, plus the natural log of A at 0 at the start of the reaction. That's equal to b. Y equals mx plus b. So again, a plot of time on the x-axis, concentrations at given time periods on the y-axis. If that is a linear plot, the slope of that line is going to be equal to the negative value of the rate constant. Whereas if you had a second order process, you know that if you plot time on the x-axis and 1 over the concentration of A at a given time on the y-axis, that's going to give you a slope that's going to have now the rate constant K, not negative K, but K alone. And the y-intercept is going to be 1 over the initial concentrations of A. So a second way, or maybe even a third way, of knowing if a reaction is first order or second order is to try these graphs generically and see which one provides a linear fit. Go ahead. On the next slide, we're going to actually try a problem. Here we go. Let's say for a second order process. So I'm telling you it's a second order process in the problem. Again, you know it's a second order process if the rate law is given to you, if the units of the rate constant are given to you, or if a plot of 1 over concentration at given time compared to time on the x-axis gives you a linear plot. Okay, so I'm telling you here, in this case, it's a second order process. You have a sample. So you have a second order process with a sample that has initial concentration equal to 1 molar. After an unidentified time period, the concentration of A is measured and is 0.25 molar. The rate constant for this process is equal to 1.24 e to the minus 1, so times 10 to the minus 1, molarity to the minus 1, seconds to the minus 1. The question is, what is the time period that's passed to reduce the concentration of A that's initially 1 molar to a concentration of 0.25 molar? We're going to solve that on the next slide here. So I have 1 over A at a given time period, the time period unknown. We did measure the concentration, so A at a given time period is 0.25 molar. That's going to equal KT, so 1.25 times 10 to the minus 1. T is what we're trying to solve for, plus 1 over the initial concentration of A, which is 1 molar. So 1 over 1 is 1, obviously. This leads to one equation with one unknown, and when I solve, T is equal to 25 seconds. It's pretty easy, right? If you know which integrated rate law to use. And the rate law equations, the integrated rate law equations, will always be given to you on an exam. Okay, in review. Well, actually, before we do the review, make sure that you can do a problem like a first order process problem. I would suggest trying problem 53 in the kinetics chapter. 53 in the kinetics chapter will ensure that you can solve for either concentration or time for a first order process. Okay, so in review, you need to be able to calculate an overall rate law. And we talked about how to do that in today's lecture. And you need to be able to use the integrated rate laws. And if you can do each of these 2 learning outcomes, you have everything you need to be successful.